So let's see. Number one. It's the question. The force between two bodies have identical electrical charges. So that could be either positive, positive, or negative, negative, or either scenario. So what should you expect from these two? Repulsion. Either one would be repulsion. Yep. We're starting off slow. Atoms having equal or nearly equal electronegativities are expected to form. Why is that in the way? It usually doesn't do that. Let's see. Somebody else joined. Oh, Josiah joined. So let me see if I can reduce that interference. It's a little better. Okay. If the atoms have nearly equal or nearly equal electronegativities, what kind of bonds will they form? Well, it definitely form covalent bonds, right? Covalent. And then the modifier to that is either polar or nonpolar. If they're almost equal, we should expect nonpolar. There's no significant separation of charge in that bond. So C would be your best answer there. For the elements cesium, fluorine, chlorine. Okay, what about them? The order of increasing electronegativity. Cesium is going to be at the lower left. So it's going to be the least electronegative. Increasing electronegativity. Fluorine is the most electronegative. So that puts chlorine in the middle. That would be B. Let's see, we're up to 4. The electron pair in the cesium fluorine bond could be considered, let's see, what do our answers look like? Closer to carbon? No. Fluorine is more electronegative than carbon. So we should expect the bond to be polar in that direction. So B, closer to fluorine because fluorine has a higher electronegativity. Yep. We found our answer. And since there are no wonky ones in there, then we can stop looking. Which of the following molecules has no dipole moment? Ooh, okay. All right. E says none. So if we find one with a dipole moment, then E can't be it. If we find one that has no dipole moment. Oh, D is all. Okay, so we need to do each one of them to find out. Okay. CO2, ammonia, and H2O. So if we're going to determine the dipole moment of a molecule, we need to know two things. Two things. One, are the bonds polar? And two, what's the geometry? Okay. So in order to do that, we have to start with the Lewis dot structure. Right. So carbon is 4 electrons. 2 times 6 is 12. That's 16 electrons. I'm going to do the electrons first. This is 5. Yeah. 5 and 3 is 8. And this is 2 and 6 is 8. Okay, that one's all, this one's none. Okay, for 16, we put carbon in the middle. because it's to the left of oxygen. Oops, I'm getting ahead of myself. Like that. That means 2, 4 minus 4 is 12 electrons. 2, 4, 6, 8, 10, 12. Used up all the electrons. Now we have to make octets. So to make an octet for carbon, and taking our formal charge into account, right, we want to keep the formal charge as low as possible. So instead of putting a triple bond on this side and a single on that side, we should put 2 double bonds. And just do like that. Now, are these bonds polar? Yeah, they both go this way. Right? Now, what's the geometry of the molecule? The SEPR says if you have 2 groups around the central atom, what format or what geometry do you have? It's linear, yeah. So this, the SEPR says this is a linear molecule. So we drew it correctly here. And these are equal in magnitude, opposite in the direction, and this is nonpolar. Okay. Ammonia, we would then put in and put our hydrogens like that. So that's we have 2 left over, and they'll go here. So each hydrogen has a duet, nitrogen has an octet, and the electronic geometry for 4, 1, 2, 3, 4 is tetrahedron. Tetrahedron. So this is that's electronic. If we want to know the geometry, we want to know the molecular geometry, we cover that one up. Say, if it's tetrahedral, then we have nitrogen here, we have a hydrogen in the back, we have a hydrogen out here, and they form that trigonal base with a lone pair up there like that. So if we cover up that one, what do we have? We have a trigonal pyramid. Now, that's not part of the answer, but it helps us. Trigonal pyramid. So, are the bonds polar? Yes, nitrogen is more polar than hydrogen. So they should be this way, this way, this way. Plus, we have that lone pair sticking out here that makes this side more negative. So all of these added together will give you a polar molecule in that direction. The water we've done so many times, we don't need to go through the option. Right. Water is bent, like, with polarity that way and that way with 2 lone pairs. So its overall polarity is this way. So we found our nonpolar, which is A, carbon dioxide. All right. Next. Looks like we're catching them all here in the beginning. 6. Which of the following has the smallest radius? Okay. I think I threw this one in here because we didn't spend a lot of time on ionic radii. We've done the atomic radii for neutral atoms. So when we look at which is the smallest radius, these are our choices. Go down to E. Yeah, E. Okay, we got argon, S2 minus, B, Cl minus, and K plus. Okay. I've got a suspicion that these might be isoelectronics. So let me look to see if argon is the neutral one. Chlorine would be isoelectronic with argon, okay? Sulfur would be isoelectronic with argon. Because all you have to do is add 2 electrons to get to argon. Potassium. Potassium loses 1, it looks like argon. Rubidium, it's off by itself. And rubidium increases the period by at least 1 for potassium and 2 for the others. So you know rubidium is going to be the biggest one. So decreasing size, let's say smallest radius, okay? It won't be rubidium. That's going to be the biggest one. I'm pretty sure about that. Okay. So if these were neutral, let's look at that first. If these were neutral, then their radius would be, potassium would be bigger than the rest of them, right? They get smaller as you go to the right, but they get bigger as you go down. Oh, that makes potassium, potassium is bigger than any one of these right here, because it's in a higher period, right? So it won't be potassium. It would, if we put them in order, let's do that. From biggest to smallest. So I would say rubidium first, and then potassium. And then we can take these in order. And since they're isoelectronic, then the with this one being the largest, now we have to go to the isoelectronics. So potassium has 19 protons. Chlorine has 17. Sulfur has 16. And argon has 18. So if they're isoelectronic, they have the same electronic structure. One with the largest nuclear charge is going to draw into the smallest radius. Okay. And that would be potassium. We can take rubidium out of the mix because it's not isoelectronic with these. It's bigger to start with. Okay. So that's why potassium is the smallest one. It has the higher nuclear charge with the same electronic structure. I feel like a lobster backing my way out. Out of that trap. All right, 7. So that makes sense of this one. Which of the following in order of decreasing size? Okay, it looks like they've all got the correct carets. They're facing the right direction. So we don't have to look for that trick. And now we have, want to look at what's available. So we have gallium 3+. We have calcium 2+. We have potassium 1+, chlorine minus, sulfur 2-. Okay, let's go down to the next one. Sulfur's already taken, chlorine's there, potassium's there, calcium, gallium. So B has all of them in it. I was looking for any strange ones. Sulfur, D, same. Okay, so all of these are covered in A, B, C, D, and E. Now we just have to put them in the right order. All right, do we have any isoelectronics in here? Well, it looks like potassium, chlorine, sulfur are isoelectronic. Calcium, lose 2, and it looks like argon. So these look like argon. Argon's not in the set, but they're isoelectronic with argon, so they have to be isoelectronic with each other. How about gallium? There's gallium. Oh, there's gallium right here. So if gallium loses 3, it's going to look like argon. Maybe not. Why? Because gallium has Ds. It has a 4p1 and a 4s2, but it also has the 3 Ds. So gallium should be pretty big. Yeah. Although, why does it say gallium is not big? All right, we're working from the assumption that these are all isoelectronic. And the electrons that they're losing are in their valence shells. But this is not isoelectronic with these guys because it has Ds. It has 3d10. But that's smaller. Let's look at this. 31 here, 20. Yeah, 19. Fluorine is 17 and 16. Okay, are we looking at the same animal? Gallium has a higher nuclear charge. And we've stripped away its 4s orbitals. It's only got the 3d10s. Okay, I think that's what the authors of this problem were getting at. Is we're still in the, we've lost all our 4s for each of these. We've added to 3. So there are no 4, n equals 4 in any of these. But this one has the highest nuclear charge. This one's next, that one's next, that one's next, that one's next. So B, that's the only thing, the only rationale I can come up with B being the correct answer. Now, the only way to prove that is to actually look at the data. You know, find the ionic radius of each one of these and check it. But logically, we're saying that B is the best answer. Okay, let's see. There's Autumn. I heard the ding. Zach here? Did Zach show up when I had my back turned? Yeah, he did. Okay. We're a full class today, then. All right. Eight. In the reaction between magnesium and sulfur, magnesium atoms what? Oh, it says becomes anions, cations, part of a polyatomic, share electrons with sulfur, crystallize. Okay. When magnesium, which is a metal, reacts with sulfur, which is a non-metal, and they're fairly far separated from each other, we would expect an ionic compound. These tend to form 2-, these tend to form 2+. So you're going to get that compound. It forms an ionic compound, which means magnesium is going to be the cation. Okay, because it's the metal. Metals like to lose electrons. Non-metals like to acquire electrons. Right. Choose the molecule with the strongest bond. All right. So let's see. It's the last one. All are equal. I find that hard to believe. F2, Cl2, Br2, and I2, correct? Right. They're all halogens. So since we don't have access to actual data, numbers for these, we have to reason that when they come together, they're going to be covalent bound. But the nuclei for each is going to be a different distance, and you're overlapping larger orbitals. So the amount of overlap, it decreases for the larger ones. You can't get that much overlap because you can't get the nuclei close enough to completely overlap orbitals. Right, so if we're looking at strongest bond, this is going to be the weakest bond. Right, then bromine, then chlorine. But if we put fluorine out here, here's the twist. Fluorine is a much smaller atom than chlorine, right? So it can have lots of overlap of its orbitals, but when it does that, it gets those 9 protons too close together, and they start to repel. So actually, chlorine has the strongest bond. That's the twist in the story. And it's because this one gets the nuclei too close together. They start to repel each other. And that means the bond has to be longer. Chlorine gives you the strongest bond. That's the best compromise between overlap and distance of the nuclei from each other. I think that's why I put that one in there. All right, now we're going to skip a few, get down to 12. Let's see. Right. These molecules have a 0 net dipole moment. All right, we're looking at that list above. Roman numeral 1 through 5. Let's do it this way. Don't have room to work. Okay. So 1 is boron trihydride. This one is nitrogen dioxide, sulfur hexafluoride, ozone, and PCl. Okay. Which one has a 0 net dipole moment? All right, so there may be several of them that had the net 0. We drew this one before, I think. We'll go through the procedure again. So that's 3 for this one and 3 times 1 for that one. So we have 6 electrons. We have boron. There. That's it. All right. If you have 3, then you're going to have a trigonal planar. Trigonal planar. Since we don't have any lone pairs, that's the molecular geometry. And it has no dipole moment. We should draw it like this. Okay. So any polarity in the bonds are going to cancel out. So this one is nonpolar. Okay, how about NO2? All right, nitrogen has 5, and then 2 times 6 is 12. So that's 17 electrons. We have nitrogen, 2 oxygens. So that's -4 is 13. Okay, 2, 4, 6, 8, 10, 12. We have 1 electron here. All right, so how do we deal with that? Nitrogen doesn't have an octet yet. We can make an octet like that. 2, 4, 6. We can't even make an octet. So nitrogen's deficient, right? But if we have 3, then it's going to be a bent molecule like this. Oops. Like that, like this, like that. So that one is going to have a dipole moment. This is polar. SF6. So we have, well, they all have oxygen. Oh, wait, that's fluorine. This is 6, and that's 6 times 7 is 42, which is 48 electrons. Okay. So now we have sulfur in 1, 2, 3, 4, 5, 6 fluorines. So that's 2, 4, 6, 8, 10, 12. 36. 2, 4, 6. 6 times 6 is 36. Use them all up if we put 6 around each of the fluorines. Okay. So we have no lone pairs to deal with. That means whatever geometry, electronic geometry we come up with is the molecular geometry. And if we have 6 around here, what's that structure? That geometry? Octahedral. Octahedral. So this is octahedral. And that's not, oh, excuse me. Put it under the wrong one. This is octahedral. And this is non-polar. Because they're all balanced. Ozone. We didn't do, this one was in the lecture, but we didn't actually draw it. So now's our opportunity. 3 times 6 is 18 electrons. So ozone would be, you know, take a pick. Which one's in the middle? They're all in the middle. So that's minus 4 equals 14. 2, 4, 6, 8, 10, 12. Work your way from outside in. We need 2 more in here, like that. Okay. Now we got to make an octet for that. So this could go double bond on that side or double bond on that side. So we would have to resonate between this one and the other one with the double bond on the other side. But for our purposes, this is really all we need. Right? For that central one, we have 1, 2, 3. That means trigonal planar, electronic. So we cover that one up. Now we have a bent molecule. So ozone is going to be like this, like that, and that. Now, I would, since these are equivalent, I would say it's non-polar, right? But we still have this lone pair out here that might give it some polarity. Although I think we're going to consider it, probably to answer the question, we're going to consider it non-polar. Let's see, is 4 part of the answer? No. Okay. So this one, we are saying this one has a net dipole, and I think it's because of that lone pair. That lone pair sticking out there gives you a negative charge on that side. Okay. So we're going to say this one's polar. And then PCl5, phosphorus is 1, 2, 3, 4, 5. 5 plus 5 times 7 is 35, so we have 40 electrons. So we have P in the middle, 1, 2, 3, 4, 5 fluorines. So that's 2, 4, 6, 8, 10. So we have 30 left over. 2, 4, 6 times 5 is 30. That's it. So we've used them all up. We have no lone pairs. And what's the structure of a 5 group trigonal bipyramid? We would have this triangle in the middle. We'd have a phosphorus up here, and we would have a chlorine here and a chlorine here, and then a chlorine at each one of them. That, and there would be a dipole, right? This bond here, this bond here. All these would be the same strength, but balance one another out. So this one's non-polar. Now let's see if 1, 3, and 5. Does that agree with B? Yeah. Okay. That's why I use the key when I'm doing this thing. because if I follow my instincts, I might get it wrong sometimes. I have found mistakes in the key that accompanies these things. And when I create the key for the review document for the exam, I take that into consideration and I correct their mistakes. Not too often. They're usually pretty good, but it does happen. I think probably because they get a graduate student or somebody with less skin in the game to answer the questions or even create the questions for all that matter. 13. All right. How many electrons must be shown as bonding or non-bonding in the Lewis structure whose skeleton is? This is an organic skeleton. So if we're going to show electrons in the Lewis structure, all we need is the valence electrons for each one. Right? So we got 1, 2, 3, 4, 5, 6 hydrogens. 6 times 1. And how many carbons? 1, 2, 3, 4. 4 carbons. Right? And then 1 oxygen. Well, 6. So let's see. 28 electrons, right? 28 electrons. Right. Simple. That was the easy one. Remember that number in case we see that thing again. Put it over here. Then we won't have to count them up again. Okay. I didn't put that one in the yellow, but since it's there, how many electrons are shared between carbons 2 and 3 of this molecule, protonaldehyde? Let's go ahead and do that, since we already have it. So we have 4 carbons, 1, 2, 3, 4. Then we have an oxygen. And then we have hydrogens. Anything else on the bottom? Okay. And these, I'm gonna circle them just so that we don't, that doesn't mean there are 1 carbon, 2 carbons, and 3 carbons. That just means that's their position numbers. Okay. How many electrons are shared between carbons 2 and 3? So we're looking at this one right here. All right, if we have 28 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We've used up 20. So we have 8 electrons. Oops. Not 80, 8. All right, so we start from the outside and work our way in. We can't put any more here. We could put some here. We could put 2 electrons here. We could put 2 here. 2 there. 2 there. Oh, I can't do that yet. Sorry. We have to work from the extremities. My mistake. We have to work from the outside in. So if we can't put any there, then we have to put them all here if they will go. All right, so there's 6 of them. We have 2 electrons left over. All right, where do they go? Well, if we put them on this one, then that'll give this one an octet. That carbon will have an octet. That oxygen will have an octet, and these will be deficient. So instead of doing that, let's move over 1 and put those extras right there. That way, we can make an octet here by doing a double bond. And then we can make an octet here for both of these carbons like that. Okay. And that says 4 bonds, 4 bonds, 4 bonds, and 8 electrons. Okay, we're good. Now the answer is how many Shared electrons between 2 and 3, 4 electrons. 2, 4. That was the trick to that. Because if you put those two over here, then these can never be resolved. Not unless you let them walk. Organic chemists do that. They do a lot of things differently. That's why I'm not an organic chemist. I teach it, but I'm not. I don't claim it. 16. If you take an organic chemistry from course from me, then I'll tell you where they're wrong. Let's see. In the Lewis structure for ICl2 minus, ICl2 minus, how many lone pairs of electrons are around? Okay, hold on a second. Let me get this thing. You know what? Let's just do that. There we go. Solves that problem. How many lone pair electrons are around the central iodine? So it tells you iodine's in the middle. All right, so we have, let's see, 3 times 7 is 21 plus 1 is 22, right? 22 electrons. Iodine in the middle. And we have a chlorine and a chlorine. So that's 4. And we have 2, 4, 6, 8, 10, 12. Well, that's 6 electrons. 2, 4, 6. So how many lone pairs of electrons are around the central atom? 3. 1, 2, 3 pairs. 6 electrons, 3 pair. All right, let's see who's next. 19. How many resonance structures can be drawn for the molecule O3? All right. Let's see if we can remember. How did we draw O3? We had here, 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 and here, right? Then put the double bond on the other side. Yeah. And we can resonate between these two. So there are only 2 resonance structures for ozone. 20. So better put the number up here. Which of the following types of molecules always has a dipole moment? All right, let's take them one at a time. E is none. So A is linear molecule with 2 identical bonds. Does it always have a dipole moment? No, actually, it never has a dipole moment. It's a linear molecule with 2 identical bonds. It will be, they'll be, even if they are polar, opposite one another, they'll cancel out. So this is nonpolar. Always. Tetrahedral, equally spaced. That's another one. If they're all identical and they're equally spaced in a tetrahedron, then they cancel one another out. C, trigonal pyramid, 3 identical bonds. All right. How do you get a trigonal pyramid? Yeah. You start with a tetrahedron. It's got a lone pair. So the molecular is trigonal pyramid, and that lone pair up there always gives you a dipole moment. Even if the bonds are nonpolar, you still got that lone pair sitting up here, and it's going to give you a polar molecule always. So we can't say none. We found one that works. And D should be trigonal planar with three identical. Yeah, that's always nonpolar also. Like boron trihydride or boron trichloride, trifluoride, those types. This is the only one that's always polar. We didn't emphasize, during the lecture, we didn't emphasize the lone pair effect as much. I think that's why I stuck these in here, so that we could get that topic, that item stuck into the topic. 21. Which set contains the atoms listed in order of increasing electronegativity? This one should be fairly simple. All right. Do we have, okay, we've got differences. We could put them all up here and then put them in order and then pick the ones out of that order. But what if we just go down the list? Like fluorine, is fluorine the least electronegative? No. A, no. Right, that one's out. Let's see, how about phosphorus, nitrogen, oxygen, fluorine? Phosphorus, nitrogen, oxygen, fluorine. Okay, that's a good start. And then oxygen, nitrogen, yeah, okay. And then phosphorus is down below nitrogen, so that's a good one right there. Yeah. And since we don't have none of the above, two of the above, that kind of stuff, we can stop because we found the right one. If we looked at the others, right, C and D both have fluorine as the highest, that's good. But then the order of the others is messed up. And then, of course, E has fluorine on the wrong end, so it's out. So we found our answer. All right, 22, right? 22. Which choice has bonds listed in order of increasing bond energy? All right. Increasing bond energy. All right. Here's where, all right, A is backwards. Now that we've got hydrogen bonded to the halogens, that hydrogen can get closer and closer to its neighbor without introducing that repulsive effect, because it's a very small single proton. So it should be the other way around. HF should have the largest bond energy, then HCl be a little less and HBr a little less. So A is backwards. This is a good one. Right? As you increase the number of bonds, you increase the strength, right? So that's a good one. They're not all the same. And we already did C. We already did that one. And that one's out of order. Right? Chlorine should be the strongest, bromine should be the weakest, and fluorine should be in the middle. So that one's wrong. And I'm just being thorough. Let's see. Dinitrogen. Okay. Here's a teaching opportunity. This dinitrogen is like that. A very, very strong bond. It's not less. The carbon-carbon bond in C2H4 is like this. Oops. Okay. Right. If we had time to do the Lewis structure, it would look like that. So actually, this one is less strong. And C2H6, C2H6 is going to be like this. Right? So actually they have it backwards. This is the correct way. They have it with the carets the other direction. All right, so we found our answer, B. Right, let's see. 23. In the gaseous phase, which of the following diatomic molecules would be the most polar? All right. Notice they're saying in the gaseous phase. They're saying in the gaseous phase because that removes any of the problems you might have with liquid interactions or crystal structure in a solid. So once they're in the gaseous phase, then you can do measurements on the actual polarity of the bond. The most polar would be where the elements are furthest apart from each other in the periodic table, right? And that's cesium and fluorine. They are the farthest apart. Cesium is, I think it's 0.7 and fluorine is 4. Right, so you could have 3.3 is the difference there. That's pretty big. That's definitely ionic, no doubt about that one. And the rest of them, they just lose because they're too close together. All right. 25. Let's see. Keep going till 1:45. Okay, I got 20 minutes. Which of the following ionic compounds has the largest lattice energy? The lattice energy must be favorable to a stable lattice. All right, remember lattice energy. Yeah. What do we mean by lattice energy? Well, if we have the cation in the gas phase and the anion in the gas phase, and I'm just using singles here. It could be double singles. It could be a mix, but for argument's sake, I'll just use singly charged. Then we get the solid, and that gives up a massive amount of energy. Okay, so the most stable is the one that gives up the most energy. How do we decide which is which? Well, of those compounds, we want a combination of high charge, if we can get it, and close or short distance. Say that, short distance. And superimposed on this is difference in electronegativity. Okay. So let's take a look at each one. We got barium oxide. We got beryllium oxide. We got cesium iodide. Oops. Is that right? Cesium? Yeah. Okay. And sodium bromide. And barium sulfide. Okay, so this is 2 plus 2 minus. This is 2 plus 2 minus. This is a 1 plus and 1 minus. 1 plus 1 minus and 2 plus 2 minus. Okay, so the largest lattice energy here is going to be with either the 2 plus and 2 minuses. So it could either be this one, this one, this one. with this high charge. Okay. So the next thing we want is which ones put the nuclei closer together. Barium and oxygen. Barium is a huge atom. It's going to be a pretty big ion also. So I would not expect that one to be a candidate, either here or here. Especially not here because sulfur is even bigger than oxygen, right? So that leaves beryllium and oxygen. Beryllium is a small 2+ ion. It's going to be able to get pretty close to that oxygen. So I would say this one would probably give you the highest lattice energy. All right. Okay, let's see, 26. The first electron affinity value for oxygen is blank, and the second electron affinity value is blank. So our choices are unfavorable, favorable. Okay. So the first electron affinity for oxygen would be what? Oxygen gas plus an electron yields oxygen like that. Right? So that's the first one. Second one would be this one plus another electron yields O2-. Okay. So if we're bringing an electron into a neutral atom, then the single most important influence is the nuclear charge, drawing that electron in. And then it gives it that minus charge. So I would say this delta H would be negative. It would give up energy. That makes it favorable. Because if it gives up energy, that means this is more stable than that. But when you try to add another electron to this negative, I would think that one would be positive. It would take energy to get that electron in here. Okay. So favorable, unfavorable. This is endothermic, this is exothermic. Now, that answers the question. It's D, exothermic, endothermic. D. But why then do we usually find when oxygen ionizes, we usually find it in that form? No. Yeah, it prefers that. And that's largely because it makes it look like neon. It completes its octet. So if you look at the energies for these two, if it's going to be stable, more stable here than here, that means that we have to give up a lot more energy here than we have to put in here. So the balance is going to be overall negative. That is, this has to be larger than that one in absolute terms. Okay, so that first electron goes in there. It gives up a lot of energy, and then some of it you have to put back to get the second electron. But overall, it's favorable. That's just trying to explain reality. Because we know what oxygen likes, and that's how we rationalize it. 27. Good. Okay, got a few more minutes. Using the following reaction data, H2 plus F2 yields 2HF, H2 yields 2H, F2. Calculate the energy of an HF bond. All right. So let's put these reactions up here. H2 plus F2 yields 2HF. And the delta H for that one, I think we're gonna have to use S for this one. Minus 542 kilojoules. Okay, second one, I'm gonna spread them out. H2 yields 2 H gas. And we have to put 432 kilojoules to make that happen. And then F2 to give us 2F. We have to put energy in for that one, 154. Okay. So if we're looking for the energy of an HF bond, how much energy does we have to put into the HF to break it? Well, the overall reaction for that would be what? HF gas yields H gas plus F gas. With it. That's our overall reaction. In order to see what amount of energy is required to break that bond. So can we combine this? Yeah, that one would be right if it's on this side, but we need half of it. So if we write HF over here, gas yields H2 gas plus F2 gas. Then we need to change the sign and take half of it. So what's half of that? 266. Did I do that right? 12. No, I didn't do that right. Let's do it longhand. Let's see, 2, 14, 7, and then 1. There we go. So we're going to use this one, and that takes care of that right there. Now, if we need to know this one, it's on the correct side, right? But there's too many of them. So what we need is 1/2 H2 gas yields. Let's see. Oh, we took half of those. We need half of this one and half of this one. I left that out. Divide this one by 2, divide that one by 2, divide that one by 2. There we go. So now this one is divided by 2 and gives us H, and that takes care of this one. So all I need is 1/2 of this one. So let's see, 2, 6, 6, right? And that's a positive. And then do the same thing for this one because I need fluorine on this side. So this one and 1/2 F2. Yes. And half of this one would be 77, right? Okay, so we're going to add this one with this one and that one, correct? Let's see if we got them all taken care of. HF, 1/2, 1/2 here, HF there, and then H here, and F here. Okay. So if I did that right, 7, 13, 14. Carry my 1. 8, 14, 21. Carry the 2. 4, 5, 6, 5, 7. 614 kilojoules. Okay. Got it wrong. What did I do wrong? I added up something wrong, didn't I? Did I do these right? I flipped it, changed the sign, took half of it. 2. That one's right. Half of this one. 12, 13. Oh. Let's check this one out.
Oh, we made 216.
216? Okay, that's where I made my mistake. Okay, you got a calculator going, right?
Yeah.
Okay, what should this be? Should it be that one now? 564?
Yeah.
Okay. Math error. Okay. So we had to use Hess to find out. And the trick to this one is saying, all right, what's the target? I mean, what's the end game? It's this equation right here. That tells you the bond energy. HF as a gas breaks apart into H atoms and fluorine atoms. Then you know where you're headed with all that stuff. Otherwise, you just might as well throw up your hands and say goodbye. Okay, got 6 minutes. Let's see, we'll probably get 28 in here. I don't know where that leaves us with the rest of them, though. As indicated by Lewis structures, which of the following would probably not exist as a stable molecule? Oh, okay. All right. And E. All right. So we know this one exists. That's methanol. CH2O, we know that one exists. That's formaldehyde. I've never seen that one before. So if I were taking the speed test, I'd know which answer to give. But it says work it out with Lewis structures. C2H4. C2H4. Oh, C3H4. There we go. Okay. So we have 4, and 4 is 8, and 6 is 14, right? Electrons. And this is 6 plus 4 is 10, 12 electrons. This is 6 and 4 is 10, and 3 is 13 electrons. This one is 8 and 2 is 10 electrons. And this one is 12 and 4 is 16 electrons. Now we can go to panel. All right, for this one, it's a little more complex than we've been used to. The way organic formulas are written, if you have a hydrogen following a carbon, those hydrogens are attached to that carbon only. And then the carbon is attached to the next atom. So that puts carbon here, hydrogen's there. And that only makes sense because you can't put a hydrogen between 2 atoms. It doesn't have enough bonds. There. So that's 2, 4, 6, 8, 10. So now we're down to 4. Right? Can't put any here. We can put them here. 1, 2, 3, 4. That's good. That works. How about this one? Carbon, and then we have 2 hydrogens, and we have an oxygen. 2, 4, 6. So we have 6 electrons. 2, 4, 6. That one doesn't have an octet yet. So we could steal like that. That's formaldehyde. Everybody knows what formaldehyde smells like, right? No? Never done a dissection in a biology lab before? No? Oh, you never forget the smell.
Oh, yeah. I had to do 5 the other day.
Yeah. Yeah, it's stanky. Okay, this one would be carbon, 3 hydrogens here, and an oxygen there. 2, 4, 6, 2, 4, 6, 8. So that's 5 electrons left. And 2, 4, 5. That wouldn't quite work because, well, all right, let's look at it this way. What is the formal charge on that carbon? Starts off with 4 as a neutral carbon, right? So it has 1, 2, 3, 4, 1 from each of these bonds. Minus 4 is 0. So its formal charge is 0. How about this oxygen? It starts off at 6 and is 1, 2, 3, 4, 5, 6. Well, that's equal to 0. Okay, that blows that argument out of the water. Um, okay. If we went ahead and did this one, we would have a carbon, carbon, hydrogen, and a hydrogen, 2, 4, 6. It's 4. And we have 2 here and 2 here. All right, so how would we make, does that do that right? 2 times 4 is 8. That's 10, yeah. 2, 4, 6. That's correct. These 4 electrons, put those there. So if we move these 2 to here, that will only give us 3 pairs or 6. So we have to move those 2 here, and that gives us a balanced. That's acetylene. And C3H4 is a little wonkier. So where do the hydrogens go? Probably here. More than likely. So that's 2, 4, 6, 8, 10, 12. 4. So if we put 2 here and 2 here, that would give these carbons octets, but that one would be deficient. So we need to move these 2 over here. That will give it 6. Move these 2 over here, that would give it 8. So that would work. This is the oddball one right here. There's no way that we can make a complete octet for that oxygen. It's got 2, 4, 6, 7. So I don't think you're ever going to see that molecule anywhere. Just wouldn't be stable. Regardless of the formal charge. That's probably why they picked it. All right. So we're up to 28.